This equation could be, mathematically, reformulated in many ways. The underlying physics wouldn't change, just the mathematics that describes it. In this version of the equation, the electric field vector is represented with the color magenta, and the magnetic field vector is represented with blue, and the gravitational field vector is represented with green. The colors I have chosen are not special in any way. Any combination of colors could be used. Each field has a numeric value. Each field has a direction. They are not just numbers, they are vectors. The small arrow above each field indicates their vector, so direction must be accounted for. What is a cross product? A cross product is a three-dimensional form of vector multiplication. When performing vector multiplication, the order of the field is important. For example, E cross B does not equal B cross E. The order is important. E cross B has a different meaning from B cross E. In a cross product of two vectors, you always start with the first vector. In this case, the first vector is the electric field vector. When you take the cross product with the second vector, it forms a curling direction. The curl curves from the first vector to the second vector. The curling direction is represented here by the curving red arrow. Using the color red for X and red for the curving arrow is my convention. When you use the right-hand rule, the third vector would point in the direction of the thumb on the right hand, upwards in this case. Instead, if the left-hand rule is used, then the direction of the third vector would be downwards. Personally, I represent the left-hand rule with an orange X, or a curving orange arrow. Negative signs matter. For example, the negative of E cross B, using the right-hand rule, is the same thing as E cross B using the left-hand rule. Eventually, when physicists start to really talk about this, then they will talk about something called flux area changes. Here's a graphic for that idea. I've described physics as being like a labyrinth. I've mentioned that one of my main goals is to show you something that lies at the center of this labyrinth, something much like a golden sphere of knowledge. In reality, this golden sphere is simply a ball of light. What I'm about to say is a critical part of that knowledge. Nature has three fundamental fields acting at right angles to each other. Fundamentally, there are three fields: the electric field, the magnetic field, and the gravitational field. And these three fields act at right angles to each other. Keep in mind, the specifics of this grand unification equation could be mathematically modified in a wide variety of ways by using a variety of constants. The grand unification equation could include the constant mu, or the speed of light, c, or pi, or the number 2, or Planck's constant, or many other constants. Just like you can transform the word hello from language to language, you can transform this knowledge with mathematics. That math might use different constants, integrals, differentials, vectors, fields, string theory, or perhaps some new type of math that is yet to be devised. In my opinion, no matter how you dress it up, with the math, underneath the central physics idea is this: nature has one unified field. It has three components acting at right angles to each other. They are the electric, magnetic, and gravitational fields. In wave theory, you can have standing waves and moving waves. A photon is an example of a moving wave. In general, when waves intersect, they can pass right through each other. Also, when they pass through each other, the waves can interact with each other. You might be wondering what makes one single wave stick together, or why would one wave be attracted to another wave? In other words, what makes two separate waves stick to each other? The physicist Heaviside and his contemporaries did not have a good theory that explained this. As they visualized the problem, they imagined that the energy would just spread out and dissipate. Let me address the first question first. What makes one single wave stick together? In my opinion, the reason the energy of one lone photon sticks together is because of how the three fields interact as one field. In essence, they are constantly pivoting around each other. Imagine two children are playing with a rope. Each holds the rope and runs around in a variety of directions. In essence, they will swing around each other, always forming a two-dimensional plane as they do so. In my opinion, something similar is happening in 3 dimensions with the 3 fundamental fields. They are like 3 children playing a 3-dimensional game of tug of war. However, they are not really 3 separate fields. In essence, their attachment is permanent. They are one field. How about the second question? Why would one wave be attracted to another wave? What makes 2 separate waves stick to each other? This has been a question men and women have been asking for ages. In order for 2 separate waves to be attracted to each other, the conditions must be right. The conditions involve the diameter of the waves, also called the wavelength, and the direction of the curl of the fields in the wave. Physicists call this direction of curl polarization. Keep in mind, these waves are made up of 3 fields, electric, magnetic, and gravitational. Macroscopic experiments show us how these fields interact. Remember, magnetic fields can attract or repel each other. Here's 2 horseshoe magnets, and I've got their north and south fields aligned, and I try to push them together, and they push away from each other. So alike magnetic fields repel. Now if I flip it over, they attract each other. This is equal and opposite. Remember, electric fields can attract or repel each other. So in this case, imagine this is a positive and this is a negative, and they're coming close to each other. They would attract. Imagine these 2 particles have the same electric field, and when they come close to each other, they repel each other. They don't stick to each other. And of course, remember, gravitational fields only attract each other. I'll demonstrate this by simply dropping this particle, and it's attracted to Earth. Simple. Again, macroscopic experiments show us how these fields interact. As these spherical waves pass through each other, if the conditions are right, then all 3 of the fields in the wave will attract each other, and the 2 waves will combine. Their attraction will simply make each wave start spinning around each other in opposite directions. So they just come together, they're attracted, and then they just start spinning around each other. If the 2 waves have the same wavelength and the correct polarization, then there's a perfect symmetry between the 2 waves. All 3 fields will attract each other. Obviously, this is very important. When all 3 fields attract each other at the same time, then this creates a very strong attraction. They become what is called a standing wave. In essence, separate moving spherical waves can combine and create an elementary particle. Keep in mind, there are all sorts of problems that might prevent this from happening. When the two waves pass by each other, they might not be close enough and just touch each other's edges. The waves might not be aligned. They might approach each other with an incompatible angle. They might have incompatible wavelengths. Their polarization might be wrong. When the two waves are aligned and actually pass through each other, there is still a range of possibilities. The waves could be 100% attracted. They might have 0% attraction. In between, there is a wide range of other possibilities, just like with people. When the attraction happens, a pattern between the two waves is created. Unfortunately, I don't have time to talk about these patterns here, but I want to give you a feel for this anyway. Here are 3 simple animations. Keep in mind, these are just 3 animations. They are mathematical. They're not physical. They are not actually electromagnetic waves. They are formed using lines in a 2-dimensional plane. They are not 3-dimensional. If you can, imagine spherical waves taking on patterns like these in 3 dimensions using the 3 fundamental fields. This attractive pattern can be divided into 3 main categories. First, this attractive pattern can be perfect. Second, this attractive pattern can have minor imperfections. It is imperfect. Or third, this attractive pattern might be only partially attractive. If the attractive pattern is perfect, imperfect, or only partial, then this will influence how stable the particle is. This gets into a discussion of how harmonic a particle is, a discussion of harmonic versus non-harmonic. This topic quickly becomes very advanced, and I can't go into it here. However, let me mention a few examples. First, particles like neutrinos, electrons, and protons appear to be perfectly stable. Second, particles like neutrons appear to be imperfect. They are partially stable. On their own, neutrons decay fairly quickly. Third, there are particles that atomic physicists call resonances. They are only partially stable. You almost need to laugh when the word stable is used. Stable hardly applies to them. They decay almost immediately after they are made. It might not even be proper to say they get made. This is a huge field. It includes particle accelerator experiments and the field of atomic physics. I would love to talk about this in more detail. However, because it takes a lot of time and this topic quickly gets very advanced, I cannot go into the details here in this science film.